There are a few ideas to keep in mind when you're determining how electrons are arranged within the orbitals of an atom. We're going to start with 3 of the ideas to keep in mind. The first one we'll look at is the Pauli exclusion principle, which says that there's only ever a maximum of 2 electrons in a single orbital. The second idea is that orbitals increase in energy with principal quantum number and the L quantum number. And as a reminder, this is what gives us the separation in energy for the different shells and subshells. Kind of like this. It's also what lets us produce this triangular diagram. And the third point to consider is that electrons, like everything, tends to adopt the lowest possible potential energy configuration. So imagine, a ball on a hill. It wants the lowest possible energy configuration, which is the bottom of the hill, right? Gravity will pull it down and it will try to minimize the potential energy. And effectively, these 3 ideas just tell you that there's only 2 electrons per orbital, and electrons are going to fill the orbitals from lowest to highest possible energies. So if you have a number of electrons, they're going to start by filling the 1s orbital, then the 2s orbital, then all of the 2p orbitals, and so on. And this covers the core concept. One subtlety to it, though, is a 4th consideration. And this 4th idea that we have to talk about is Hund's rule. And Hund's rule says that when you fill degenerate orbitals, the lowest energy configuration comes when all the spins are aligned. And really what this means is within any subshell, you're going to put all of the spins in the same direction. And it's easiest to see what this means in an example. So consider putting electrons into a p subshell. So within a p subshell, you have 3 different p orbitals, px, py, and pz, and all 3 of them are degenerate. They all have the same energy. So if you want to put a number of electrons into them, the way to maximize the energy is to put the spins in aligned. So that means that you put 1 electron in each orbital before you start pairing up the orbitals. So that means you'd have something like this rather than something like this. Even though both of these p subshells have 3 electrons, the one on the left has all 3 spins facing in the same direction, so all spin 1/2 or all spin minus 1/2. And the example on the right has spins paired. That is, in the px orbital, you have 1 spin plus 1/2 and 1 spin minus 1/2. So when you're filling a subshell, put all the spins in aligned and then start pairing them. So if we wanted to add 4 electrons to the p subshell, we would add 3 spin aligned and then you would add a spin opposed. And if you wanted to add a 5th electron, you would add it to one of the unpaired electrons, and then a 6th. So we'll do a couple of examples of electron configurations. So electron configurations are simply the arrangement of electrons within the orbitals. And there are a couple of different ways to represent these. One is by drawing box-style energy level diagrams, and the other is by writing out orbital designations. So we'll do a few examples, and I'll show you both representations for each example. So the hydrogen atom has 1 electron. That's it. And the lowest energy possible orbital is the 1s orbital. So you would write the 1s orbital, draw it as a box, draw your potential energy axis, and add a single electron arrow to that box. So this would be hydrogen's box diagram electron configuration. Its orbital designation representation would be 1s1, where you have the 1s representation, which is the principal quantum number, and then the subshell, and the little number at the top right hand side represents the number of electrons in that orbital. Hydrogen only has one electron, so 1s1. Helium has 2 electrons. So again, you draw the boxes to represent the orbitals. So we put our very first electron in to the 1s orbital, and then we look and we decide, are there any other degenerate orbitals that we can put our second electron into? No, there's not. There's only one orbital at this energy level, so we can pair up our second electron. And we could also write this using the other format as 1s2. So the 1s orbital with 2 electrons in it. Lithium has 3 electrons, so our box diagram is going to get a little bit more complicated. Now we'll need access to 2 orbitals. We add our first electron, and we look around to see if there are any other orbitals at that same degenerate energy level. There aren't, so we can pair up that electron. And now that orbital is full. We can't add any more electrons to it, so we have to look at the next highest energy orbital, and that's where we put our third electron. And we can represent this as a 1s2, 2s1 electron configuration. And beryllium with 4 electrons is almost identical. And with boron, now we get, again, slightly more complicated because now we have access to the 2p subshell. We'll do 2 more examples. We'll do carbon first with its 6 electrons. And now that we have multiple degenerate energy levels, so all of the 2p orbitals, we don't pair things up automatically. We start filling each orbital with spin-aligned electrons. And our orbital designation format is 1s2, 2s2, 2p2. And we'll do one final example with a lot more electrons, just to show you what it looks like once you start adding the d electrons in. We'll look at titanium with its 22 electrons. So titanium has 22 electrons, and we fill from the bottom up. So we add starting at the 1s orbital. And you can see that for titanium, we don't have an entirely filled 3D subshell, and there are actually no electrons in the 4p subshell or in the 4d subshell that I haven't drawn yet. And we can also write this using our orbital designation system. So at this point, it's worth noting that the only subshell that will not be filled is the very final subshell, the one furthest to the right. The 3D subshell is only partially filled, and everything to the left of it, everything to lower energy, is going to be completely filled.